Okay, so yesterday we talked about general solution stuff. Today we're going to talk about solutions that involve a precipitate. All right, so there are really three general types of solution that we need to worry about. Precipitation reactions we're doing today, acid-base reactions that always result in a salt and water, and then redox reactions, which take about 10 pieces of paper and really look scary, but aren't so bad, and make you feel really, really smart when you're all done. Okay, so a precipitation reaction is a double replacement reaction where the reactants are always solutions, so they're always aqueous. And the products may be aqueous or they may be a precipitate. So you can have the two aqueous reactants make two aqueous products, and when we see that, we call that no reaction, because really nothing happened. Because the reactants, if they're aqueous, are going to break up into ions in solution. The products, they're aqueous, they break up into ions in solution. So the ion soup that you have is the same. So if you took these two aqueous things and put them into a beaker, you would have sodium ions, you would have chlorine ions, you would have potassium ions, you would have nitrate ions before and after the reaction. So we call that no reaction. You can have the two reactants make a solid and a aqueous solution, and then I guess theoretically it's possible you could have two reactants that are aqueous make two products that are solid. I can't really think of how that's going to work, but it could. Okay, so very nicely for you, the rest of this page is just a rehash of what we've done in the net ionic lab. So to predict the outcome, to see which one of these scenarios you have when you mix the reactants, you have to determine the ions. You have to write a proper formula, crisscross, and then you have to decide whether or not you have a precipitate formed or not. So let's go with this first one, potassium nitrate plus barium chloride. If I'm right, and I think probably you should too. They tell us these are both aqueous. Aqueous means that they form ions in solution. What I'd like you to do is predict the products. Anyone? Potassium chloride and barium nitrate. Okay. Now, the trick that we have been taught is to ionize and then crisscross in an attempt to write a valid formula, because we still try to pull those subscripts across, and you cannot. So these will be paired together as KCl, and then these two will be paired together as BaNO3, 2. And actually, one would say BaNO3 taken twice. All right. Now, you have to determine the state of solubility for these two products, and you should be able to do that bippity-boppity-boo. This has a group 1 cation, so it is automatically aqueous. This has a nitrate. All nitrates are aqueous, so there you go. So you would say that this is no reaction. There is no new solid formed. All right, sodium sulfate and lead nitrate. Anybody like to take a guess? You did this. Maybe it was just one of the 105 that you did and don't remember. Sodium sulfate and lead 2 nitrate ionizes into this. Need to do a little balancing. Actually, I need to do a little balancing on the last one. I just forgot. State of matter. This is a solid. Let us, yeah, that is correct. Let's remember how we took a balanced equation and made it into a net ionic equation. Remember, anything that is aqueous can be ionized. So out of these 4 species, the only one that cannot be ionized or broken down into ions is this one. So we'll start with our reactants. If you look at sodium sulfate, there are 2 sodium atoms and 1 sulfate polyatomic ion. So to form ions, you would have 2 of the sodium ions, 1 of the sulfate ions. Then what here?
2 of the nitrate.
Right. It would look like this. And then here, 2 sodium ions and 2 nitrate ions, and then the PbSO4. It does not break apart. Now, this is a complete ionic equation. We'd like the net ionic equation. The difference between the complete and the net ionic is to cross out the spectator. Remember, a spectator ion is defined as anything that looks exactly the same on both sides of the arrow. So the sodium ion here and the sodium ion here are exactly the same. Sulfate ion here is different than the sulfate that's in this compound. Ditto with the lead, and the nitrates are the same. So the net ionic equation now, when we were doing that lab, we were just looking qualitatively at the solids that were formed. Now we're going to be looking quantitatively at the solids that are formed. So we saw that lead sulfate is formed here. If we switch cations here, we're going to have lead 3 hydroxide and potassium nitrate. Potassium nitrate is soluble. So we just went through the molecular equation, which is the full balanced equation. We talked about the complete ionic equation and how to get to the net ionic equation. I don't know. I left it where you left it. I didn't do a lot of cleaning up. Okay, now here is the part where you find it? Good. The part where you start to do some quantitation. So to do these problems, your steps for success always starts with the same step 1. Write the balanced equation. And then you should probably remember that to do some stoichiometry, you're going to take the molarity, multiply it times the volume, and that's going to give you the number of moles. You can use your stoichiometry from that. Determine which reactant is limiting. Oh, great, that didn't go away either. Calculate the grams of product formed by the limiting reactant. Well, if you can do this part, you probably can do this part. So let's start with this one. I need more room. I did not give myself enough. Do you have a calculator? When aqueous solutions of sodium sulfate and lead 2 nitrate are mixed, lead 2 sulfate precipitates. We knew that. Calculate the mass of lead 2 sulfate formed when 1.25 liters of 0.05 molar lead 2 nitrate and 2 liters of 0.025 molar sodium sulfate are mixed. So step 1, write the balanced equation. Okay. Now, you remember we could do the mole fact right here off of the coefficient of the balanced equation. 1, 1, 1, 2. What we need is to put our given up here. And we're not quite ready for our given yet. We have to do some calculations. So I would like to know the number of moles of the Na2SO4. And all I'm going to do is take the molarity, there we go, times the volume.
Why are you saying that there's only 2 moles of,
I'm taking the mole facts just from the balanced equation. Okay. What do I have here? Thank you. 0.05 moles of that, so I'm going to put 0.05 here. And then the number of moles of the lead nitrate. And 0.05 and 1.25 is and a naked number. Okay, now let's figure out the limiting reactant, even though you can see the limiting reactant, but let's do, anyway. All right, I would like to know, so the half of mole of the Na2SO4 over its mole fact will produce how many moles of PbSO4? Why did I choose that product? Because they want to know the mass of it. And it's a 1-to-1 stoich, so I can produce 0.05 mole of the lead sulfate if I use up all of the sodium sulfate. And then the lead nitrate is going to be so the limiting reactant is the sodium sulfate. So I would like to know the number of grams of lead sulfate equal to, well, I know how many moles of lead sulfate are going to be produced. 0.05 moles of lead sulfate. I know that 1 mole of lead sulfate is equal to its molar mass. Lead is 207, sulfur's 32. There are 4 oxygens that are 64, and it is 303? Okay. 303 grams. And that should get us to the correct answer, not the answer that's published right there. Anybody? 15.2. Okay. Get that?